Hello again. In this notebook, we are going to cover Torch Autograd. This is automatic differentiation that comes with Pytorch. In fact, automatic differentiation is the main reason to use frameworks like Pytorch because they allow differentiation on these tensors. And the reason it is very useful or very handy is because under the hood, neural networks use an algorithm called backpropagation. And backpropagation is nothing but the differentiation chain rule that you learned in high school applied to these tensors over and over again. All right. So we are not going to explain the backpropagation algorithm in this course because this is a short course, but we cover it in great detail in our course, Deep Learning with Pytorch. That's a paid course. But in this course, we will just see how automatic differentiation works in Pytorch. And then we will go over, I'll briefly explain how the algorithm called backpropagation works. But first, let's focus on automatic differentiation or Autograd. Now, this requires a little bit of math. It requires you to know about very basic calculus. But if you don't know, you can refresh it by Googling. We'll pick a very simple example where things will be easier to understand. Okay. So now, before we get started, we have to install this package called TorchWiz. TorchWiz allows us to visualize the computational graph that Pytorch uses internally to represent how gradients flow. Okay, and we'll see an example. So you have to install that. Next, we basically import Torch, and then we import matplotlib so that we can plot certain things. Now, when we run a neural network, there are two things that happen. One is called the forward propagation. So basically, imagine that you have a lot of computation going on where you have the input, and inside this neural network, there are many numbers. They are called weights and biases. They get multiplied and added to the vector, right? You can imagine the input as a vector, as a tensor. And there's a lot of computation that happens, basically multiplication and addition, and then you get an output. If the output is not, this process of taking an input, which could be an image, and running it through the network is called forward propagation. Okay. Now, during forward propagation, the weights and biases, which are the parameters of the network, they are not changed. All right. On the other hand, once we receive the output, right, and we know we can look at our training set, which basically contains the input and the output pairs. And if the output is not what we expected, it means that the weights, the parameters of these neural networks, they need to be updated. So how do we update? We update it using this algorithm called backpropagation. And the way to update it is we look at how the output changes with respect to the inputs. In other words, if you calculate the gradients, right, how does the output change? If there is, and this error that you notice at the end, right? During the training process, we have the actual output that should happen, and we have this output that we are currently getting. We take the difference of those two things, and we say if the output is large, then we change the parameters of this network in such a way that the next time the outputs are better, right? So it's basically learning again and again. And for that, it needs to do something called backpropagation. And we'll see a simple example of Autograd, how at each step, for backpropagation to work, at each step of the network, we need to calculate the gradients, okay? And that is what we are going to show in this notebook. Okay. Now, take an example. Let's say we have this function, z equals x times y plus y squared, okay? And we want to calculate the partial derivative of z with respect to x. Because z depends on x and y, we can calculate the partial derivatives of z with respect to x or y, okay? And when we say partial derivative, it means that if you want to calculate the partial derivative with respect to x, you treat y as a constant, as if these things are constant, and you take the derivative. So in this simple expression, you can see that if you keep y as constant, if you take the derivative of a constant term, it is 0. So this part goes to 0. And when you take the derivative of x with respect, when you take the derivative of z with respect to x, this term simply becomes y. So the partial derivative of z with respect to x equals y. And the partial derivative of z with respect to y is you keep x constant, right? So it is x, and this differentiate this with respect to y, this becomes 1. And differentiate this with respect to y, it becomes 2y, okay? So we have partial derivative of z with respect to y is x plus 2y, all right? Now, if you have specific values of x and y, let's say 2 and 3, then you can calculate the gradient of z with respect to x will be, you just plug in the numbers. It's basically whatever the value of y is, right? Which is 3, okay? That's great. Now, if you want to calculate the gradient of z with respect to y, then you have to do x plus 2y, which is 2 plus 2 times 3, that is equal to 8. Now, for doing this kind of computation, internally, Pytorch uses, it basically picks every little computation and puts them as a node in a computational graph. For example, we have z equals xy plus y squared. Then internally, it would create this node p equals xy. So to do this computation, then it will create q equals y squared for this computation. And then it will add the two things, right? Then z equals p plus q. So if you look at the graph structure, we have x and y. These are called leaf nodes. And then we have this multiplication operator so that x and y can be multiplied. We have this to the power 2 operator, squared operator, so that y can be raised to the power 2. And then these two things come together in an addition, which is this one. And then we get the value of z, which is p plus q, which is nothing but xy plus y squared. So this internal graph, right, at each step, when it knows how the computation is being performed, right, and therefore it can actually calculate the partial derivative of z with respect to x or z with respect to y, because it has this entire computational graph. So let's see how this is done, okay? If you want to know exactly how this thing worked, you can see, you can follow this expression, how we got y and how we got x plus 2y. This is straight out of high school. Whatever calculus you had learned in high school, it is sufficient to derive these, right? And if you do not know these, you can just Google up and see basic differentiation, and you will find how this differentiation works. All right. So now let's look how Pytorch does it internally. So we are going to create two tensors. X is equal to 2, 5. Okay, this is a vector. We have y equals 3, 7. All right. So we have two vectors. Z equals x times y plus y squared. All right. And now let's basically sum this z. Okay. When we do sum, it basically sums the elements of z. As you can see here, when we do this operation, z is basically a vector containing two elements. To calculate the gradients, we need to use backward, this function called backward. And this works only on scalar quantities, right? It doesn't work on vectors because it doesn't know how the elements need to be combined. And that is why we do z.sum. Z.sum basically converts that vector into a scalar, right? It adds all the elements of z and creates a single scalar out of it. And then we can use this backward, which is, doing backpropagation and calculating the gradients. Now, as we know that if you do this, we know this expression, and so we know that what should be the, and we know the values of x and y. We also know that the gradient of x or the gradient of z with respect to x, which is x dot grad, is essentially this expression. It is y, right? So whatever we passed in here, we will see that it should be, it should show up here. You can see that the gradient it calculated, this is the value of y, okay? And the gradient for of z with respect to y is x plus 2y, okay? X plus 2y. So if you go and check this, you will see that x plus 2y, right? X is this. So the first element is 2, x plus 2y, 2 times 3. So that is 8. So we got 8 here. And then x on the second element of x is 5 plus 2y. 2y is 2 times 7. So it is 5 plus 14, which is 19. So we got 19 here. So this computation happened automatically. We did not do it. Internally, it created this graph structure, and then it did the computation. Now, there is another one. If you do z.grad, it would show that there is no gradient, right? But if you have a big graph and you want to calculate the intermediate gradients also, which can be very useful when you're debugging something, then typically you just have to, it basically does gradient calculation only for the leaf nodes, which are these nodes, right? In the end. If you have an intermediate node like the z, the number z here, it is not going to store that gradient for you, okay? So, but if you want to actually have access to that gradient, all you need to do is do z dot retain grad, which means that it is going to retain that gradient. The reason it doesn't retain a gradient by default is because it uses more memory. When you are trying to do these gradient calculation and trying to retain all this, it takes more memory, right? So if you run this again, you will see that the gradient of z, obviously the gradient of z with respect to each itself is 1, and that is why we see 1 and 1 here, okay? So so the results of the operation is that you can look at this result, what is finally stored in z. We know that z is x times y plus y squared. If you do this calculation, it will show 15 and 74. So we got the gradients, we got the value of z, etc. Now some details we have to actually specify. If you want to do gradient computation, then you have to put at the leaf nodes here, we have to actually say it requires gradient. The reason is that again, storing this information, calculating these things, it's expensive. So by default, the gradients are not calculated, right? The gradients are not, the variables are not stored in such a way that you can calculate gradients on them. And that is why we want to explicitly say require gradient, right? And if you don't do it, we can see what happens. Let's see, lower down here, we say required gradient is false. If you do that, if you try to do z dot backward, you're going to get, you're going to get an error that those gradients were not stored. So the last thing to keep to notice here is this method called detach. Why did we use it? The explanation is right here. So if the detach method is used to create a new tensor that shares the storage with the original tensor, but without tracking the operation. So it gets detached, right? It is not, the gradient calculation doesn't happen. So if you actually print this require grad, right? Z dot requires grad, it is going to say, it is true, right? That the requires grad, that variable is true. So it's going to do all the computation. But now let's say you detach it, right? You say z dot det equals, z dot detach. Now, this is a new tensor, but this doesn't require grad, right? So this is useful when you want to perform operations on a tensor without affecting the computational graph. So you can detach it and create some operations. You can debug, do whatever, but it doesn't affect your computational graph. So that's what detach does. Now let's visualize this, right? We have created this graph, and we are going to visualize it using TorchViz. So TorchViz, the way to visualize this is make underscore dot. You may be thinking that why doesn't it call it visualize, or something like that. So dot, this is a program that comes from GraphViz, and nobody really knows why why the program is called dot. Why is it not called visualize or something like that? There are several theories why it is called dot. Some say that it is some say it is description of things, as DeepSeek told me it is description of things, but ChatGPT told me something else. So we don't know. So nobody knows actually what this dot means, but this is a visualizer. Okay. So make dot takes in the final output, right? This is the output of the computational graph and the parameters that you want to visualize. So we want to visualize X, Y, and Z. And basically we do dot render and give it a name, and it's going to output this thing in PNG format, right? And this is what you will get, right? This is the computational graph that that we are using. Okay. We already covered how to detach tensors, and we also covered why requires grad is essential, because without this, it's not storing any gradient information. You will not be able to do the backpropagation. All right, and it will give you a runtime error. So now finally, let's just cover a little bit of backpropagation. Now, if you actually take our course Deep Learning with Pytorch, that is a paid course, we go into great detail about backpropagation, all the technical nitty-gritty into as to how it works. But here I'm just going to give you a basic idea, right? Just a hand-waving idea. So gradient, right, of let's say we have a bowl. This bowl that you're looking at, this is the loss function. So loss function in deep learning essentially means some function of the error you're making, right? Let's say you have the photo of a cat, and your network is outputting that it is a dog. Then you have made a mistake, right? You have made a mistake, and you have many training examples to show that a mistake has been made. And this network, this whole network that you have created, you know the parameters. You have different weights, W1, W2, etc. There are actually millions, sometimes billions of these weights. And we want to see how changing a certain weight, right, or certain combination of weights, it actually changes the loss, right? Ideally, think about the neural network as a black box, and these weights are knobs on this black box. When you have the right combination of weights, when you have the settings are right of these weights, then the black box works perfectly. It, when you input image of a cat, it says that it is a cat. But when the knobs are not right, then you don't get the right results. So how to make the knobs right? That's the process of training. During the process of training, you show it many images of cats, dogs, etc., and look at the output. And you know the output beforehand. So you can compare what the network is outputting and what the real ground truth is. If they don't match, then go and change the weights, right? But you don't change the weights randomly. You could change the weights randomly, but the training would take a lot of time, right? So what you do is something called gradient descent. Now I'm just showing you how it works when there are only two weights. But in practice, there are millions of weights, right? There are millions of weights in any neural network, but the basic idea remains the same. So if you can compute the gradient of the loss of this error function, based on the weights, with respect to the weights, just like we calculated the gradient of z with respect to x and y. That gradient is actually the direction of the slope of this error function. Okay, so let's say you are at this point, right? This is some value of w1 and w2, right? You're at this point, and you are able to calculate the gradient of the loss function with respect to w1 and w2, which you do by passing many images through the network. You can know which way this error function is decreasing, which way the error is decreasing. And you can follow this path to the bottom of this error function, and that will give you excellent results, right? So that is the whole idea of training, is to find the bottom of this error surface. Now this surface can be very complex. There can be multiple minima, etc. But at the core, the algorithm is simply that I can use backpropagation to find these gradients. Based on the gradient, I know how to change the weights. Once you change the weight, you calculate the gradients again, and you keep doing that until you reach the bottom of this error surface. So that is basically backpropagation, right? Here, for example, we are showing that this is what a neural network looks like. A very simple neuron is just the basic element of a neural network. And when you show an input is essentially a vector or a tensor, and this could represent image, it could represent sound, voice, sound, it could represent text, it could represent anything, right? So this input, when it enters this neuron, right, the computation we do is we multiply the input with a weight, and then we add a bias to it, okay? And the output is this term, right? Y equals wx plus b. Now this, if the weight is right, and we are showing this very simple computation for only one neuron. There are billions of neurons in a neural network, and we are showing the computation for only one neuron. Imagine you had only one neuron, right? In that case, the output would be wx plus b. You check whether the output is correct or not, and based on the error this makes, you can basically backpropagate the gradient and figure out, how the error is changing with respect to the weight. And that gives you a mechanism to update this weight. So you update this weight, and this process continues, right? You give it a new input and see how the weight needs to be changed, so that for all inputs, for all images in the training set, or for all pieces of text that are in your training set, this error keeps decreasing, right? And the way once you reach the bottom of the error surface, you know that the training has completed. There are other things that you need to take care of. I just explained it in the most simplistic way possible, but that's essentially how backpropagation works. You can read through this explanation also. It will be essentially what I mentioned, and you'll get a sense of how backpropagation works. But if you want to know the details, the technical nitty-gritty, then I would encourage you to join our paid course. So that brings us to the end of this notebook. We'll see you again in notebook number 3.